Hello friends, in the previous video we have seen that addition of two function is also integrable. Now in this video we discuss about subtraction of two functions, whether the subtraction of two function is integrable or it is not integrable. This is the about this video on your screen. If f1 and f2 are two integrable bounded and integrable functions on closed interval a comma b, then f, which is a subtraction of 2 f1 minus f2, is also integrable on closed interval a comma b, and integration of f1 minus integration of f2 equal to integration of f. Exactly with the parallel lines of sum plus we will show this theorem. Okay, so first we can see that as two functions are bounded, then the function f, which is a subtraction of these two f1 minus f2, is clearly a bounded function since these two are bounded. Again we consider this f equal to f1 plus of minus f2. Okay, f1 plus of f1 plus minus f2. Let capital M I dash comma small m I dash capital M I double dash comma small m I double dash semicolon capital Mi comma small mi are these bounds of are supremum. These are the bounds supremum and infimum of f1, f2 and f respectively. Okay, if this is the bounds of f, this is bounds of f1, these are the bounds of f2, these are the bounds of f. Let us consider there one set. Suppose my set contain these 2 point, 3 point, 1, 2, 3. Then you can see that upper bound of this set is 3, lower bound of this set is 1. That means this is capital M, this is a small m. And if we take the exactly reverse order, that means if we subtract this minus 1, minus 2 and minus 3 multiply by minus, then this minus 3 is the smallest number. So minus 3 is a lower bound and minus 1 is a upper bound of this. So here we have small m equal to minus 3 and capital M is equal to minus m, and therefore the bounds of minus f2 are here capital Mi double dash is infimum, this is an infimum, and this minus with minus sign, and minus small mi double dash is a supremum of this function. Then the rough bounds of this function f are these are the supremum and infimum. So we have capital Mi dash minus small mi double dash, and here small mi dash minus capital Mi double dash. Again we multiply and take a summation, multiply by delta xi small mi dash delta xi, I vary from 1 to n, minus capital Mi double dash delta xi, I vary from 1 to n, less than equal to small mi into delta xi, I vary from 1 to n, less than equal to capital Mi into delta xi, I vary from 1 to n, less than equal to summation of capital Mi dash into delta xi, I is equal to 1 to n, minus summation of small mi double dash delta xi, I vary from 1 to n. Okay, what is this? This is a LPF1 minus this is UPF2 less than equal to LPF less than equal to UPF less than equal to UPF1 minus LPF1. So we arrive at this inequality, and now if we take the subtraction of the upper and lower bound using the criteria, as we know, whenever 2 is less than pi u is less than 7 less than 10, 2 is 5 less than 7 less than 10, then obviously 7 minus 5 is less than 10 minus 2. Then we arrive at UPF minus LPF is less than equal to UPF1 minus LPF1 minus LPF1 plus UPF2. Okay, so here you can see this is a F2, then that is, this is equal to, we can write it as UPF1 minus LPF1 in one bracket and UPF2 minus LPF2 in another bracket. Now use the definition of integrability of the function f1 and f2. As functions are integrable, since it is given that f1 and f2 are integrable, as f1 and f2 are integrable over close interval a comma b, then for epsilon greater than 0 there exists partition P of close interval a comma b with norm mu of P less than delta, such that we can take u f1 minus LP f1 is less than epsilon by 2. Similarly, UPF2 minus LPF2 is less than epsilon by 2. This gives us UPF minus LPF is less than epsilon by 2 plus epsilon by 2 equal to epsilon, and hence the function is integrable. Okay, now let us move to the second part of this theorem, where we need to show that the integration of f equal to integration of f1 minus integration of f2. Again friends, let us apply the Darboux condition. If f1 and f2 are integrable, then by Darboux theorem for epsilon greater than 0, epsilon greater than, there exists partition P of close interval a comma b with norm mu of P less than delta. We have UPF1 is less than equal to integration of f1 plus 1 by 2 epsilon, and LPF2 is greater than equal to integration of f2 minus 1 by 2 epsilon. Okay, then integration of the function f is less than equal to integrate upper sum of f, but upper sum of f is less than equal to upper sum of f1 minus lower sum of f2. We have seen this in the previous inequality. Okay, but this is less than equal to integration of f1 a to b plus 1 by 2 epsilon minus integration a to b, right? Here minus LPF is less than equal to, this implies that minus LPF is less than equal to integration of f2 plus 1 by 2 epsilon, right? So here we get integration plus 1 by 2 epsilon, and what it gives us, this gives us integration a to b of f is less than equal to integration a to b f1 dx minus integration a to b f2 dx plus epsilon. As epsilon is an arbitrary number, this result is exactly equal to less than equal to integration of f1 minus integration of f2, right? So we arrive at this result, integration of f1 is less than equal to integration of f2. Proceeding with minus sign, instead of f1 f2 we take minus, we replace f by minus f1 minus f1 by minus f1 and f2 by minus f2 in this. So integration of a to b minus f into dx, integration a to b minus f1 into dx minus integration a to b minus f2 into dx. Again multiplying throughout this by minus sign, we get integration a to b f dx is greater than equal to integration a to b f1 dx minus integration a to b f2 dx. So this is equation number 2 and this is 1. Now from integration 1 and 2 we have integration a to b of f equal to integration a to b f1 dx minus integration a to b f2 dx. Okay, so this is not possible. At the same time one quantity is greater than this quantity and at the same time this quantity is less than this quantity. It is possible only if these two are equal. Okay, whenever the equality hold, the equality hold means we have integration of f equal to integration of f1 minus integration of f2. So we have shown that if two functions are integrable then their subtraction is also integrable.